In the earlier class we have seen the 3 processes: steam methane reforming, partial oxidation, autothermal reforming, their comparison. Now any of these processes can be combined and then we can have a combined reforming as well, bi-reforming, tri-reforming based on what are the oxidants, how these are combined, all those we will see in today's class. In combined reforming we have a primary reformer which is a smaller fire tubular reactor, and then we have a secondary reformer. So the partially reformed gas from the primary reformer, it goes to the secondary reformer and we can get the desired gas composition. Now let us look at the process. Natural gas is pre-treated. So desulfurization, in the desulfurization unit, after removal of the sulfur containing contents, it is preheated and along with the steam it is passed into the primary reformer. So this is the primary reformer, wherein it undergoes the reforming reaction. So the syngas which is partially being reformed, it is passed through the autothermal reformer, the secondary reformer, undergoes the processes, various processes that we have already learned now. The outlet gas from the secondary reformer is to be cooled. So heat which is generated, excess of heat which is there in the syngas can be utilized for steam generation, and the remaining, so the gas, syngas then thereafter can undergo the various gas cleaning steps, water gas shift reaction, so as to finally get the desired product. Now after the water gas shift, it will undergo the purification steps to separate the various other constituents other than hydrogen. There is reformer, primary reformer, then there is a secondary reformer. Now this primary reformer is a steam methane reformer which operates under mild set of conditions. That partially reformed gas goes to the secondary reformer, which is an autothermal reformer. Usually the method of combined reforming, wherein 2 different processes are combined together so as to get the desired H2/CO ratio, and that could be used for various applications like whether it is ammonia synthesis, whether it is methanol synthesis, and with this the use of steam could be reduced. Another method of reforming is dry reforming. This is also known as carbon dioxide reforming or stoichiometric reforming. The difference between the earlier processes and dry reforming is, here carbon dioxide is used as the oxidant. So feedstock, that is methane, is reacting with the oxidant which is carbon dioxide to produce syngas. The important thing here is that both the feedstock and oxidant, they are greenhouse gases. So if we are using them, then we are in fact reducing, we can say that we are reducing the carbon footprint, or if the natural gas which is used for the dry reforming, it has a higher CO2 content. So the natural gas, if it is already having a higher CO2 content, rather than going for gas cleaning, that can directly be used for dry reforming process. Now one of the thing that needs to be seen here is methane, which is a highly reduced form of carbon, carbon dioxide which is highly oxidized form of carbon, are reacting together so as to give the syngas. The hydrogen to CO ratio as can be seen is 1, or it can be less than 1. In ideal case it is 1, but it could be less than 1 also. We will see under what conditions. The reaction delta H value suggests that it is endothermic, and value positive sign shows it is endothermic, value suggests that it is even more endothermic than the steam methane reforming reaction. The reason for high endothermicity is both the feedstock and the oxidant, they are relatively inert. So, this is the stabilized form which if they have to react, then an activation energy is required to make them to react. So, that is why high energy is required, it is a highly endothermic process. With this H2 by CO ratio of 1, it may not be a desired method for hydrogen production. However, this is a method of hydrogen production wherein this syngas which is being produced can directly be used for various processes, various oxo processes like production of acetic acid, synthesis of dimethyl ether. Syngas can be converted into olefins using Fischer-Tropsch process to olefin reactions. So, these are the applications wherein the syngas which is obtained after dry reforming can be used for. If you see the possible reactions that occur in dry reforming of methane, so methane reacting with carbon dioxide producing syngas, that is the primary reaction, that is the major reaction that occurs. Other than that, the various other reactions that can occur includes the reaction wherein certain amount of hydrogen is being consumed in the process, and the carbon dioxide which is oxidant also consumes the hydrogen which is the product which is obtained to produce CO and H2O. The other reaction is, so it is consuming more hydrogen. Now, this reduces the product, the hydrogen in the product obtained. CO formed can also consume hydrogen to produce methane. So, this is the methanation reaction. The second and third are methanation reaction. So, dry reforming of methane occurs in the temperature range of 900 to 1200 degree centigrade, and the hydrogen to CO ratio, like striking, if you look at the reaction, it is ideally it is 1, but this can be somewhere lying between 0.7 to 1.9, and this can be selected based on what is the oxidant to feedstock ratio. Based on what is the CO2 to CH4 ratio, this can range somewhere between 0.7 to 1.9. So, although it is a dry process, the name itself suggesting dry reforming of methane, it is a dry process, but we can see that certain amount of water is obtained on the product side. At the same time, we can also add some amount of steam to the process, and that has an advantage, that addition of steam will reduce the carbon formation. Since carbon dioxide is used as an oxidant, so the carbon formation is the major bottleneck. So, both endothermicity of the process and carbon formation, these are the two major bottlenecks towards the industrial use of the process. This carbon formation can be reduced with use of appropriate catalyst, support and promoter. It can also be reduced by including steam, it can be reduced by having proper dispersion of the catalyst onto the support by using promoters. Now, the various catalysts which are used in the dry reforming process are, they can be either non-noble metal catalyst like nickel or other nickel based catalyst, which can be on supports like Al2O3. This is the most widely used catalyst and support combination. It can be nickel, magnesium, aluminum or nickel cerium. All these catalysts, nickel based catalysts, have shown to have a very good methane conversion. The major problem with the nickel based catalyst is they have a very good initial methane conversion, they have good activity, but the coke formation is higher in nickel based catalyst, and we can add up certain promoters like potassium subpromoter can be used to increase its life and stability. There are other non-noble metal catalysts like copper, cobalt, iron, they also show good activity and they can be used preferably in a bimetallic catalyst, like they can be used in together with a noble metal. Like for example, nickel and cobalt, they are used along with noble metals as a bimetallic catalyst on an alumina support. Compared to non-noble metals, noble metals they have a higher activity, they provides better conversion and they have good resistance towards coking and sintering. So, they have a good thermal stability and mechanical stability, they are less prone to coking and sintering. If we see among the various noble metals, the order of their reactivity could be rhodium higher than ruthenium, higher than iridium, and it is more than that of the even the nickel, which is used widely in the as a catalyst. Platinum, palladium, they have higher activity compared to the cobalt, iron and copper. So, noble metals definitely they have better activity, they are stability, they provide good conversion and selectivity, but the cost is the major problem here. To consider to address these issues, like to get all these simultaneously and cost effectively as well, a small amount of noble metal like rhodium, ruthenium, iridium, platinum, palladium or gold can be added to the non-noble metal catalyst like nickel, cobalt, copper, iron, and that can provide together stability, catalytic activity, higher conversion at a reduced cost. Now, there are several catalyst combinations, bimetallic catalysts like nickel iron, nickel cobalt, they show very good stability. Nickel cobalt, they show higher conversion, nickel platinum, they show higher activity and reduced coking, and these other than these noble and non-noble metal catalyst, transition metal based catalyst, perovskites are also used as catalyst with noble metal doping. We know that other than catalyst, support is also very important because it serves several purposes. The various supports which have been used for dry reforming of methane includes alumina, Al2O3, TiO2, ZrO2, Nb2O5, CeO2, Ta2O5, La2O3, ZrO2, a combination of the supports ZrO2, La2O3, magnesium oxide, alumina along with magnesium oxide, silica, yttria, Y2O3, zeolites and SbA15. Now, all these they have a separate characteristic. For example, if we see nickel on alumina, then these have good conversion, methane conversion. Nickel can be on a zirconia support, so it has good oxygen mobility. Nickel, when it is with magnesium oxide and alumina, they have better stability as well as activity. And similarly, the others noble metal based catalyst like rhodium on alumina, they show lower coke deposition. So, there are various combination of catalyst and support which could provide good performance in terms of activity, selectivity, conversion, reduced coking and sintering. Now, this we are using carbon dioxide as oxidant here. So, the problems associated with carbon deposition are more severe in case of dry reforming of methane. There are various reactions that can result into catalyst deactivation by means of carbon deposition, like the Bodard reaction wherein there is CO is disproportionation can give CO2 and carbon deposition. Now we can see that this is a reaction wherein it is favorable at lower temperature. Reduction of CO can result into carbon formation. This again occurs at a lower temperature, but the Gibbs free energy of this reaction is not favorable. So, it is not a preferred route for carbon formation. There can be methane decomposition, this occurs at a higher temperature, favored at a higher temperature. Even reduction of carbon dioxide can occur to produce carbon. So, there are several ways in which carbon can formed, but this carbon which is formed can also be removed. Any of the reverse reactions out of these can result into removal of the carbon formation. There could be gasification of coke which is formed, which can reduce the carbon formation. The use of appropriate support and promoter and catalyst can reduce the carbon formation. The support can provide desired basicity, which instead of supporting carbon formation like decomposition of the various species, it can support carbon gasification. So, the appropriate support, catalyst and promoter use can reduce the carbon formation. At the same time, it is observed that it depends upon what is the temperature and carbon dioxide to methane ratio. It has been reported like carbon dioxide to methane ratio, if it is stoichiometric, say it is 1:1, then the carbon formation is lower for temperatures higher than 1100 degree centigrade. If this ratio is 2, then the temperatures above 750 degree centigrade for reduced coke formation. If it is 3, then temperatures above 700 degree centigrade results into lower coke formation. So, both the temperature as well as the CO2 to methane ratio are important in how much amount of carbon is being formed with the various reactions taking place in the process. The carbon which is formed, that can be of different type. It could be either whisker form of carbon being formed, and this whisker type of carbon, it is formed usually in the catalyst which are aged. So, which has undergone several cycles. So, after catalyst aging, this whisker type of carbon becomes more prominent, and this carbon which is formed, it diffuses. The problem with the whisker carbon is that as it is formed, it onto the catalyst surface is diffuses inside the catalyst, it reaches the catalyst and support interface. So, as it is formed on the surface, it diffuses inside the catalyst, it reaches the interface between the catalyst and support, and with time this lifts the catalyst. So, catalyst is lifted from the support. So, there is a breakage of catalyst that will happen, and that will also block the catalytic bed as the catalyst will be removed from the support. And this is the most problematic form of carbon which is formed in the dry reforming of methane. The other form of carbon is pyrolytic carbon, and this is usually formed in case of higher hydrocarbons. And the third one is the gum which is formed. So, this is in fact several layers of carbon is being formed, CHX material. These are layers of graphene type of carbon which is formed on the catalyst. Now, out of these 3 forms of carbon, the gum carbon is formed at a lower temperature, and the viscous and pyrolytic carbon or the coke, these are formed at a higher temperature. But the most problematic out of the 3 carbon formed is the whisker type of carbon, and this is promoted at a higher temperature, lower S/C ratio, lower steam to carbon ratio. So, if we use higher steam to carbon ratio, the coking tendency will reduce, and in the presence of aromatics. Now, which of these species out of these whisker carbon or coke or gum will be formed, that all depends upon the thermodynamics of the process. It also depends upon the catalyst substrate interaction. All these are going to decide the species which are formed in the process. At the same time we know that what is the shape of the catalyst, what is the size of the catalyst, how good is the dispersion, how good is the support catalyst interaction, what promoters we have used, all those also determine the catalyst deactivation or coking tendency. Like if small size of catalyst is being used, high surface area is being used, we know that the dispersion, if the dispersion is higher, then the coke formation will be lower. So, small size of catalyst and high dispersion is desirable to reduce the coke formation, and we require appropriate operating conditions, temperatures and pressure, so that the catalyst deactivation should be lower. But then there are challenges that we have seen in detail in the steam methane reforming, that if we use very small size of catalyst, then the pressure drop will be there, and so there should be an optimum between the size of the catalyst, and like it should be not be very high and it should not be very low, and that is determined by the heat transfer as well as the pressure drop inside the bed. There are two processes of dry reforming which have reached to the commercialization state. These are Calcore and Spark process. Now in the first process, which is Calcore process, it is designed to achieve a particular H2/CO ratio which could be used for various downstream applications. So the H2/CO ratio which is preferred in the process is 0.43, and the nickel catalyst is used under the carbon dioxide partial pressures. The second process, which is Spark process, this is a process wherein the H2/CO ratio, wide range of H2/CO ratios are achieved, and this is achieved in a way wherein sulfur poisoning is done intentionally to reduce the ensemble size. To reduce now the H2/CO ratio, to get a wider range of H2/CO ratio in this process, the activity is altered of the catalyst, wherein intentionally sulfur poisoning is done by means of H2S, so that the ensemble size becomes smaller, and the possible H2/CO ratio that can be achieved could be varied in that process. But then such processes have issues, like if the later catalyst and all, they have a tendency towards sulfur poisoning, then that can lead to sulfur poisoning of the downstream process catalyst. At the same time it will reduce also the catalyst activity. So that was about the dry reforming of methane. Now we can have several other combinations of oxidant being used to perform various reforming for certain selective applications, like bi-reforming. In bi-reforming, oxidant which is used is steam and carbon dioxide. So the methane, if we see the bi-reforming for feedstock, which is methane, it reacts with carbon dioxide and steam to produce syngas, and the syngas which is produced is in the ratio of H2/CO ratio is 2 here. Now this is the primary reaction which can occur in bi-reforming of methane. Other than that, there are several other reactions that can also occur. The reaction wherein carbon monoxide reacts with water, steam to produce carbon dioxide and hydrogen, this is the well known process which we have seen earlier also several times, water gas shift reaction. It can undergo dry reforming in the presence of carbon dioxide, which is an oxidant being present. So methane can react with carbon dioxide producing syngas, again dry reforming of methane. So the carbon dioxide, which is oxidant, can react with the hydrogen product to produce carbon monoxide and steam. So this is the reverse of water gas shift reaction that can also occur. Methane can react with substoichiometric amount of oxygen to undergo partial oxidation producing syngas. Carbon monoxide disproportionation can occur, that can lead to carbon formation. Methane can decompose to give carbon and hydrogen. So other than the primary reaction that we have seen, there can be several other possible reactions that can occur during the bi-reforming of methane. The H2/CO ratio is 2, and this can be further adjusted by selecting the steam and steam carbon dioxide ratio, or we can say the steam and methane or carbon dioxide and methane ratio can be selected such that we can get the required H2 by CO ratio. The operating temperature in the process is between 700 to 950 degree centigrade and pressure between 10 to 30 bar. Now the advantage of bi-reforming is that here again we are using the greenhouse gases to produce hydrogen or H2 syngas in the desired ratio of hydrogen to carbon monoxide, and this hydrogen to carbon monoxide is such that the required application, it can be used directly for the various downstream production processes. Compared to the dry reforming of methane, here the carbon formation is comparatively less, and thus the reduced catalyst deactivation will be obtained because we are using steam in the process as an oxidant as well, and that reduces the coke formation in the entire process. So herein we have used two oxidants in the bi-reforming. There are two processes, they are occurring simultaneously. So there are like it is the reforming with steam reforming as well as dry reforming. Now if oxygen, steam and carbon dioxide, all three are used together, so it can undergo either partial oxidation, it can undergo combustion, it can undergo steam reforming, it can undergo dry reforming. So methane, if it is the feedstock, it can undergo steam methane reforming producing syngas, can undergo dry reforming reacting with carbon dioxide to produce syngas, or it can undergo oxidation reaction to produce carbon dioxide and steam. So these are the major reactions occurring in the tri-reforming. Other than these three reactions mentioned, there can be several other possible reactions that can occur. CO reacting with steam to produce CO2, methane undergoing partial oxidation to produce syngas, carbon monoxide disproportionation reaction, methane can undergo decomposition. So other than the primary reactions, these are the other possible reactions which can occur. The operating temperature for tri-reforming is somewhere 700 to 1000 degree centigrade in between, and the pressure of operation around 20 bar. The H2 by CO that can be achieved can be within 1.2 to 1.5, and there are various catalysts that can be used for the tri-reforming process like nickel, palladium, iridium, platinum, rhodium, and supports like aluminum oxide, magnesium oxide can be used for the process. To summarize what we have seen today, we have seen that various greenhouse gases can be utilized for reforming process either to produce hydrogen, or if the H2 by CO ratio is not appropriate, then that can be used for various other production, various other chemicals or various other Fischer-Tropsch liquid fuels production processes. But when we are using carbon dioxide as an oxidant, we have seen the major problem is related to the deactivation of catalyst. However, that can be reduced by appropriate selection of catalyst, promoter, support. We have seen that the steam to carbon ratio can be adjusted. We can see that the operating temperatures also defines like how much will be the carbon formation or coke deposition, and we can have through these processes either combined refining or dry reforming or bi and tri reforming various H2 by CO ratio processes that can be used for various downstream processes. Thank you.